Okay, so today I'm going to give a talk on a joint work with my former master thesis Daniel Krieger, and actually this project started with his master thesis, and then Thomas Nagler was just a betreuer. He helped me with the supervising of this master thesis, and after submitting, we still worked, I think, 3 years on this project, and finally we could publish in Journal of Econometrics, but it was very long actually to do it. Before I start my talk, I would like to maybe ask you who knows copulas? Just raise your hand. Not many people know. Okay. And who knows wine copulas? Okay, few people know about it. I can talk about wine copulas in more detail because as you see already here, we have the copula models, the wine copula models, and we are talking, I will present you today the model for the multivariate time series. Okay. Now this is actually the overview of my talk. So I will briefly introduce copulas because as you know, I will introduce wine copulas. I will maybe just briefly review some classical time series models, and then I will present the market model based on the wine copulas. Statistical interests people are using and very short. Okay, so when I was a postdoc, in many talks I have heard that in 70s and 80s, graduate students wanted to construct multiple distribution with marginal normal distribution, but the joint distribution is not normal. 70s, 80s, you don't have Google, you don't have ChatGPT, and if you supervise thousands of flat theorem, I think you are out of the business. And many people, I think these people are, I think one of them was a professor in Harvard, he said they failed. They could not construct a multiple distribution, which is joint distribution. I mean, it's not normal, but the marginal distributions are normal. And exactly, I mean, the answer to this question I will show you on slide. And just to fix our notation, what are copulas? Copulas are actually nothing else than multiple distributions on the unit cube. Yeah, it means you have just multiple distribution, uniform, marginals are uniform. Yeah, and the famous flat theorem actually says that if you have any multiple distribution function, then there is this copula C, which I do not claim here that it's unique, such that you can couple marginal distribution with this copula function, and you will obtain this multiple distribution function. It means the complicated problem of modeling multivariate distribution, you can split into 2 subtasks. In the first task, you can model multivariate univariate margins, which is the known problem, and then you couple them with copula C. If the marginal distributions are uniform, then the copula C. Okay. In my talk, I will always consider absolutely continuous multivariate distribution. This means actually the density of the lambda vector x is given just by differentiating d times. You have copula density times the marginal distance. This will be important for the presentation of the wine copula models. And so it means if now you have some multiple distribution and it's continuous, then using this you can very easily construct copulas, and this is the formula which means what it could be. I take multiple normal distribution, I can extract the copula of it, and then I combine it, for example, with the univariate of the T distribution, one dimensional T. This is answer to the question which posed on the first slide. What we see here, you get the bivariate normal distribution. In this slide, you have actually the Clayton copula, which combined with Gaussian margins. I mean, in each margin, if you consider marginal distribution, it will be standard normal. But as you see here already, it doesn't look like multiple normal. And if you would like to see really how it looks this distribution function, actually for the Clayton copula, how does it look here? And if you look now at the counterpart of the densities, this is nice ellipse spelled ellipses here, and here you see it doesn't look as a normal distribution. Okay, so and why copulas are important? Because uniform marginal distributions somehow can influence, the picture of the dependent structure. And here you see a very simple example. I have here multivariate, sampled from the one distribution where exponentials, when margins are exponentials. And here you have margins are Gaussian. And if you look at here, you would ask, okay, it looks like independent. But if you look at this picture, you see here that there is some more action here. And it could be something like you see, okay, maybe it's dependent somehow. Yeah? Maybe this line, maybe this line, if you do regression. But if you now transform x1, x2 is there through univariate distributions, you will obtain this so-called copula sample. And here you see that the data is actually independent. The margins are independent. Okay, so this was actually the First, very short presentation about copulas. Are there any questions? Okay. Now I will talk about wine copulas. So the point is the following. If you consider bivariate copulas, the class is very rich. But as soon as you go to dimension d larger than 2, it is very difficult. You can have maybe Clayton copula, you can complete mountain generators, you can construct Archimedean copulas, T copula, Gaussian copula, and that's all. And then actually what I will talk today, I will present you actually construction of multiple copulas using just bivariate copulas, which are called pair copulas. And to construct them, we have to consider graphical objects, which we call vines. And there are different types of vines, so for example, D vine, C vine, L vine. We call our copulas S vines, and it's also accepted in the literature. Even that it is because of stationary vines. I know there is all the Y vines, yeah. If you have two responses, yeah. And how was the story about the vine? The story started actually from Harry John, 1996. He posed a question: I have a copula, yeah. And now multivariate copula. Now I would like to somehow characterize this. Can I characterize this copula just by having its bivariate matrix or serial matrix, or maybe bivariate serial matrix? In that time, he recognized that even if you know all bivariate margins, it is not enough to specify the copula. What you have to know some conditionals, not just bivariate. For example, for dimension 3, you have 1, 2, 2, 3, and 1, 3. But he also recognized you need also maybe 1, 2 given 3. Yeah? It was actually Journal of Material Analysis, 1996, and he worked on the terms of the distribution functions. Afterwards, Bedford and Cook, they worked on they considered densities. They could really solve this problem. They really actually said, okay, I mean, not solve, but they introduced the notion of the vines. I mean, regular vines. They showed that you can represent the multivariate density as a vines. I mean, but this actually what they did here. It was very nice theoretical result, but application was actually not so good because your conditional density always depends on the conditional value. It means if you have conditional value, it means you have each time consider new copula. And the real application, I mean, the usefulness of this result by Aleksey and Cook was actually discovered in the paper by TRR, the chart of Gates and Bakken, yeah, 2009, where they introduced the vines. What they did here, actually, you can construct actually multivariate copula using bivariate copulas, yeah. And you can even mix Gaussian copulas, Archimedean copulas, and all the stuff. For example, if you know Archimedean copulas, you know that usually you have some restrictions. If you consider hierarchical Archimedean copulas, and you have restriction on the dependence coefficient. If you have monotone functions, then all the parameter is always the same. Yes. If you would like to learn more about vine copulas, you can look at the chapter's book, Electronic Statistics. She's going also to give now the second, I mean, some point not now, but at the moment 2019, which is textbook on the vine copulas. And there are numerous L packages which developed by former physicians of the charter. It is Ulf Schepsmeyer, Thomas Nagler also did a lot, and we have actually very active research on the on vines at our department, technical university. Okay, now I would like to show you how we can construct multivariate copula of dimension 5 using bivariate copula. Yeah? I mean, it's called subdimension D1 because it's just drawable. It's a very nice draw. What we have to do here, if you look at dimension 5, we need to actually 10 bivariate copulas, what you see here. And it would be also the same if you, for example, have correlation coefficient. If you have multivariate normal distribution of dimension 5, yeah, some standard normal margins, then in order to define it, you need actually 5 off-diagonal correlation coefficient. It's also the same amount of the parameters, but here you have functions, correlation multiplication correlations. Yeah? What we will do here is the following. I mean, we look always at the right-hand side, and if I do in the right-hand side, I mean, of course, I'm properly choose the copulas and the arguments. On the left-hand side, you will get a valid copula. Okay? That means we are talking about the word. Again, it's construction. What did I do? First of all, I will take 4 bivariate copulas. And these 4 bivariate copulas, I will start, I mean, I'll do the V1 and so on here. And how you can determine them? I can determine them using this graph. I have 5 variables. I just put along one line. I have 5 nodes. And now I just connect them. Yeah, no loops here. And what I will do here, for example, if you have node 1 and 2, yeah, you label all the edges. If you just want to 2, 3, you label it 2, 3. Okay. In this way, I know how to write. In this case, sure, you can do it a bit differently. The most important thing you don't have to, yeah, and then I will have see a different stuff. In the next step, what I will do the following: I will take these edges and they become now nodes. Okay, take 1, 2, here, and now it means I have 5 nodes in the first tree, and each time I will decrease by 1, and then I have to somehow connect them, and I'm allowed to connect 2 nodes only if they in the previously they share one as edges they share 1 node. For example, I'm allowed to connect 1, 2, and 3 because edges 1, 2, and 3 they share node can do. And in this case, actually, it's unique. I mean, if you have divine, I mean, actually, everything is unique. You don't have any. And so it means now you see here in the next step, you see here, it means the next 3 copulas which I need, it will be the copulas, I mean, 1, 3 given 2. Why I know it is this one? Because if you take the nodes here, yeah, and now I would like to label the edges, and now the common element I put after this straight line, I mean, as a conditioning set, yeah, and different elements I put as the before. You will always have 2 different elements, yeah, and afterwards we have 1, 2, or 3 condition 1. And this is 1, 3 given 2, and exactly this copula, actually what you see here, what I will take it, it is actually the copula of the conditional distribution 1, 3 given 2, yeah. And this is exactly what hydrogen also recognizes. It is not enough just to have copula 1, 3. You have to know conditional copula 1, 3 given 2. And now, since it's conditional copula, it means the arguments of this copula not just uniform distributed random, should be uniform distributed random variables. In order to get it, what you have here, since I know C12 density, I know distribution function, then I can also compute what the conditional distribution 1 given 2. And this is exactly what you construct here. And the second, I think what you see here, this copula is absolute, means you can just parametrically define, but the conditioning, the arguments of the condition of this copula, their conditional distributions, and they always depend on the condition value. So this one, the same story is 2, 4, and so on. In general, this conditioning distribution, I mean, 1, 3 given 2, I mean, copula should actually depend also on the condition value U2, but we drop it here. I mean, yeah, and exactly this was exactly the main achievement, yeah, of the paper from 2009. They showed if you drop this dependence, you still get a valid copula. It's a valid distribution. That's the point. Yeah? Otherwise, it is not. And especially why you see it, because if you consider normal distribution for normal distribution, you immediately see that you don't need actually the conditional value. Because if you consider 3-dimensional normal distribution, conditional distribution, expectation depends on the conditional value, but the correlation coefficient doesn't. That's exactly what it is. How you put. Okay. In the next step, now again the same story. Now if you 1, 3 given 2, 2, 4 given 3, this edge labels becomes nodes. Again, I connect these 2 guys because they share 1 node here. And now I would like to again label it. And what you see here, you can give 1, 3 given 2, 2, 4 given 3. The different elements are actually 2 and 3. The information value up here, and sorry, common elements 2 and 3, 2 and 3. Yeah. And 1 and 4 are different, they will appear. And this is actually what you see here. It is the copula of the conditional distribution, 1, 4 given, I mean, actually the density of the term. Yeah? And it describes, and then the same story with the argument. You can write down here the argument would be 1 given to 3, 4 given to 3 argument. You'll see later that this argument, I mean, I will not show, but this argument can be then, you can show that you can in nested manner represent as using bivariate copula. I mean, using this. And the last one would be actually this copula 1, 5. Okay, questions? Huh? Yeah. Okay, if it is clear, then I will continue. And this is actually the construction of the copula. I mean, how I can construct the 5-dimensional copula using the bivariate copula density. Now I have to somehow yes.
So you just recalled that one often drops the conditioning arguments, and I totally see the argument for the normal case. In general, if I'm not mistaken, so this is what we call like this simplifying assumption.
Yes.
If it's called an assumption, then this tells me that well, it can also not be satisfied. Otherwise, like it would be a vacuous assumption. So maybe are there situations in which we do pay a price for making this assumption and dropping the conditioning arguments?
Okay, so it's a very good question actually. Yes, this is a non-simplifying assumption. The point is the following: in general, conditional copula depends on this, and there are some research that people showed. For example, for Clayton distributions, the multivariate assumption satisfied, but sure, for some distributions, it's not satisfied. What we did actually here, we tried, for example, we took the data which simulated from one copula, and we tried to check with another decompositions. And you saw the difference in the local likelihood actually was more. In general, again, this we have to consider as a way of construction of multivariate copulas. Yeah? And sure, if you do not do the simplifying assumption, then actually any copula this can be represented this way, any. But it will be very huge part, yeah. But then for each conditional value, you have to always assume in you maybe copula which depend on this parameter, and this was actually natural to assume K. It's not something like I consider this question in this way. I'm not considering whether it is satisfied or not. I just have a construction which solves this problem with a flexible one. I don't have any other tools to do it. I just start from here. I assume that the condition copula does not depend, and I will come to the left-hand side. But otherwise, you're right, it is a lot of research at the moment to check and to see. But if simplifying assumption is not satisfied, then we have to consider copula, which depend on the conditional value. And it means now I have the variable 2, 3, and 4. For each of the values, I have each time another copula density. And then it means actually the problem then becomes something like how many points we have, so many parameters, so many functions, and it's too large more. Okay, so I usually always consider from this side, and from this side I would like to, model. I would like to find. Therefore, I usually do not question whether this assumption is satisfied. I know that it is in general. If it was satisfied, it would be very nice. And any density I could have done this. I will come to this point also. I think later you will see that. Now I would like to show. I draw here a very simple D1, and now actually. This was actually exactly what Bedford and Cook did. They said, okay, so we consider the so-called regular ones, R1, what is the regular one is collections of the trees. What means collections of the trees? You have here just connected acyclic graph, which means you do not have errors, yeah, and they are not connected. And each time we construct the T1 is a tree with vertices V1 and edges V1. The vertices are actually represented as the variables that you have. You connect them in such a way. For the first tree, you connect in such a way that it should be connected in no loops. In the next step, what you do here, all labels, yeah, from the tree T1 become vertices, yeah, of the second tree T2, and then we have to satisfy proximity conditions. We are allowed to connect edges in the next level only if previous level the edges come from one node, like what we have here. This is called proximity conditions. Okay, and here one example, for example, edge level I will write here AE and so on. Here we see here AB from V1 and is not from the D. And if you take the variables and delete from the end, you should do the subset of the data. Here I should say here maybe the notation. In the book by Charter, she uses the semicolon because she very deeply goes in this. For me, it is not important because I am just know it is a copula of this conditional distribution. Therefore, I am using this straight line here. Yeah? But I know many people are using the semicolon. Yeah? Okay, so one example: 1, 5 given 2, 3, 4. And this was the 1, 5 given 2. Okay, so this was about y's. And then here's the 4-dimensional cy I would like to show you. And on this 4-dimensional cy, you see here, I have here 1, 2, 3, 4. It is something like star form because I put this point here. And now I connect them 1, 2, 1, 3, 1, 4. In the next level, what becomes here, I have 1, 2, 1, 3, 1, 4 at the node levels. And now I have to connect them. In this case, actually, if you see here, actually I should connect here all of them. Because if you look 1, 3, 1, 4, 1, 3, 1, 3, and 1, 4, they share one node, I could connect them. But the point is, I have here 3 edges. In the next level, I have to have 2 edges. In this case, it means I have to make a choice out of 3 what I would like to choose, and here we choose let's say 1, 2, and here now again the same story, and then here it is now like the D1 something. Okay, it means whenever you have a situation that from one edge you have more than 2 edges, always you have now a choice. Okay, how you will proceed next time. you have to always decide, okay, what you will, which actually you will obviously 1, 2, 3, and here we only. This was actually from another paper where we modeled the exchange rates. Here I have 7 variables, and using so-called this one algorithm. I mean, what we do here, you just check, okay, what is the candle style, power candle style is the highest. And here I know I have to decide here on should also get the connected 3. I mean, yeah. And the next 3, what I can do, I can compute all the conditional distribution, I mean, conditional distribution, because I know Copulas, and then using this first, I can compute the candle style for this, for this middle class one thing I can do this. Okay. This was exactly the best of in proof. This was exactly the question that you say. Actually, any Copula CO, any distribution function, I can have done this way. I mean, I got to clear on this, the Copula. And what you see here is this depends on the condition, this depends, but Copulas also depends on the condition y. Okay? That means this holds for any Copula test. But what we do now here, if we delete this, we assume that, I mean, if data depend, then this representation still gives me a valid Copula test. This was exactly I think this is a crucial point. The simplifying assumption what you see here, and sure the check it actually for normal distribution it works, and then if it's for normal works, why we cannot assume it? I think it's my opinion. Yes. Okay, examples, student, Gaussian. For the student Copula is also the same. I mean, you can show it because that depends. I mean, and then also you have, yes. And now we have the following. Because if I will talk about Wine Copula models, I always assume I have V, I mean, vines, I mean, and then I have the sort before, yeah. And then associated to each edge, I have one vine Copula. Copulas, okay. And this is what I talked about vine Copula. Vine, and for each edge, I have one Copula which I have. And what may be nice to know is side remark for you. If you have regular vine, and on this regular vine, you consider partial correlations. And you can, Dorota Kurovitska showed with Roger Cook that there is one-to-one correspondence between correlation matrices and partial correlations on the regular. It's a very nice result because you can, I think they use it in order that if you have some matrix which is not positively defined, what you can do here, you consider some vine, transform everything to the partial correlations, and you will get some problem. Maybe the row is too large, yeah, and you just then make it smaller, and then you can make valid okay. And I use actually this. For the MCMC, also very easy to do MCMC because otherwise it's very difficult to check whether the correlation matrix or not valid. Yeah. Okay, this was actually about vines and Copulas, and now I would like to just maybe very briefly say about vector process. I think many of you know about it. If you have just partial Gaussian vector after the two processes here, I mean X is stationary. If you take X1, X2, I mean first of all that, and shift in time, power, yeah. For translation equivalence, somehow the distribution should not change, yeah, of the XT in computational. So for the Gaussian was here XT is equal to the here. We want some matrix, actually T is some covariance matrix, and the most important thing actually is it's the roots of this factorization polynomials are actually outside of this unit circle, then XT station. You know about this. So what you can do here, I can write down what the joint distribution of the x6 minus 1. You know what is the upper covariance function, gamma 1, and it's actually very good. And you can do also for any if you consider any results. Okay, this is very nice because here you have Gaussian distribution, and this means if I have the Gaussian distribution, I also expect a Gaussian Copula, and it is linear time series because you have to add the sum. And already I think a lot of people said, okay, how we can do it that we don't have Gaussian distribution. I think I know a lot of papers by Remignac, and what he said, okay, why you have to consider this representation with the following, you consider x1 and x2, yeah, put together, and the joint distribution of this vector is t, of dimension 2 times t, with some given the given parameter mu, vector mu location parameter and covariance. Again, if you would like to have this vector stationary, what you do here, you are simply sigma 1 is equal to sigma 2, because it will be the covariance of the x1, covariance of the. But now I would like to have somehow after regressive processes, and so therefore this is here. what is it? Actually, if I know x1, you consider x2 given x1 distribution, and this you can compute for the t distribution. Yeah, there is a formula, and you can take it, and here you see here now it will be again t of the dimensional t distribution. Here you have the degrees of freedom parameter, you have the allocation parameter, you have the I call it the association parameter because of all the different points of view. And here's the relationship. If you condition d variables, you know the for t distribution usually increases exactly by this d. You have here sigma 2 1 and you have here the covariance matrix. Yeah? And what you see here, the covariance matrix depends on the okay. And now, okay, sorry, it depends on this one, but again, it's the covariance matrix. But if you change it to the correlation matrix, and you know the correlation matrix, then because not the covariance, the most important is the correlation matrix for. Yeah. Okay, and if you can do it, it means what we can construct here. We can construct it now after a regressive process where each marginal distribution is t, yeah, and it's not normal questions. And the joint distribution of the x1 and xt you can write down in this way because if I would have to give after the regressive process of order 1, what we do here x2 to 1. X3 given x1, x3 given x2 because after the of order 1 is only the remaining part. And so on. And each of these guys are already computed here. I mean, I know what it is here. And this means I can write down the log likelihood. If I can write down the log likelihood, I can estimate this model. Yeah, I can simulate from this model. Okay, questions? Okay, then I will continue.
How would they generalize to higher order processes? So if it's a bar P,
you want this one?
No, the general idea.
I mean, you mean IRP mode process. It's very easy. You just then you write x1, x2, xp. Yeah, I mean, it will be not d, it will be p times d. You have to consider one more, p plus 1, and you consider conditional distribution x2 given the remaining part. Huh? Or maybe you do this classical trick. If you var p process, you can write down as a var 1 process, if somehow you do it. But I didn't also consider because we usually always say, since in the classical case, you can always do this transformation, but I think you can also write down this because of stationarity. I know these guys are equal, and I think it should be possible. Okay, actually, we already worked on the copulas and how to construct the nonlinear time series, but it was just univariate case. I think it was with Michael Smith in 2010. In our JASA paper, we already said, okay, if you would like to simulate, I mean, if you would like to have a model using one copulas, you would like to have a model such that the joint distribution is not, dependent structure is not given by the Gaussian copula, yeah, and you have some process of the order IRP. And we did exactly using this, using vines. And then Michael Smith continued the idea. 2015, he got the next paper. What he said, okay, I have now, starting from now, I always assume that I don't consider the margins. I just consider copula data. Yeah, sure, I know that you don't know the margin, but you can just maybe non-parametrically estimate or maybe parametrically estimate and change it here. So I have now ut is the vector. And the first in this T indicates actually the time point. The second one is the dimension 1D. Now, what he did the following. Michael Smith said, okay, I consider each variable and write down a very, very long file. 1, 1, 1, 3, 4 variables here for the first time point, 4 variables for the second time point, this one, and he connected them. He connected in this way. Sure, you can connect also in this way also. Yeah? But his idea was to get very long dy, etc. And if you have very long d1, all others is 1, 1, 1, 2, 1, 1, 1. And now what you see here, you have 1 and 2, two different time points, and exactly this copula will describe means the cross-sectional, cross-temporal dependence. Temporal dependence. Okay, so you can write down everything down. And he did all theory. At the same time, actually the topic was very hot because 3 groups independently worked on this problem, it looks like. And B and CO, it was a paper in Journal of Time Series Analysis. They said, okay, we will consider this type of device. And again, you write down all variables, all vectors as a very long one, but the decided to have this type. It looks like M, therefore we call it as the M line, or they call it line, and they were the following. And now they say the following. And now next time in the first case there is no problem. You connect it. Yeah? In the next time, if you would like to write down for this guys, it's actually no problem. You can write down. The problem is actually here. You have 3 edges coming out of one node, and now how will you proceed? Yeah? And what they said, they said, okay, look, we consider always two adjoined trees, and always this considered as a long divide. Then it is clear that we have to write down this guy. If you consider this as a long divide, you have to consider this one and so on. Each time as you come to the edge where you have more than 3 nodes, they're always okay. I consider this as a divide. I can write down the next one. I consider this as divide, and I will write down this one. And then they got unique. I mean, again, so the first one was the long divide, the second one was the M-vine, and then Brakeman and Charles, what PhDs of each other, they considered T-vine. They said, okay, we would like to have star structure because we analyze a lot foreign exchange data and all the stuff, and usually you have one very important foreign exchange, for example, euro to dollar, and then all the remaining somehow maybe driven by this exchange rate. And here you see the variable 1, yeah, and derives all other variables, variable 2, and again 1 derives. Then afterwards, they wanted to go down, and what their idea was the following: they wanted to keep the structure of C1, therefore you have here C1, but at this point there is some, and this was exactly would be a big problem because in order that this model gives you a stationary time series, you have to also check some assumptions on. I mean, you cannot just arbitrarily define Copulas as you want. You have to settle some something. I will talk about this model with data, which something you have to do. And this was exactly yes. And afterwards, I supervised about 3 master thesis on this topic. And in the first topic, I got very good master student, Daniel Krieger, and I said, okay, look, everyone considering different y's. Why we do not generalize it for any regular y? Just consider any y, yeah, and connect it as you want. And this is one example for 5 dimensions because you have to go to dimension 5 in order to differentiate between C and dy's, and we connect it as we want, not just here and this way, but we can connect it this way, just one here. And what we can do here, can you write down, because we have also software for this, and the question was, can you write down also the matrix or the and to understand the whole stuff. Yeah? Okay, and yes, and he could do it. I mean, in his master thesis, I mean, this part was solved in the master thesis, and here is the idea how we proceed. Okay, the point is the following: we would like to take line structure such that, I mean, yeah, under practical conditions, yeah, you always get stationary time series. What is practical condition? For example, if I have dependence between variable 1 and 2, then I just shift it. I mean, copula. I shift it in time. For the second time point 1 and 2 should be the same, and so on. If you have between 1 and 4, you shift it in time, you have to also get the same. In general, if you have different time points and different time points and 3 variables, in general, you can connect it as you want. It is valid line. I mean, it looks like a loop, but it's because if you just put it down, it's first one, second one, third, fourth, fifth, and so on, it's actually. It is not really a loop, it is just from equal here and then write down. And if you consider var process, for this var process, you can really write down what should be paired right down. But this one is not practicable, yeah? Because you cannot check this assumption, because here I can depend this first variable and the third variable in the time point 1, time point 2, and then I have to check again this assumption for the next one, but I don't have this guy coming here, and how to do it. And the idea was the following. We said, okay, the first importance is actually we first of all have to construct points for one single time point. Just one time point, we have to solve it. It could be D1, it could be C1, if it was going to the larger dimension, it could be any RY. And because of the stationarity, you would have to check it, what you will do, because for each edge, I will assign one copula, and for the stationarity, this copula should be the same also for all other time points. Yeah? You just copy it. We have here, copy it in this way. The next time point you will continue, you will get here. Yes, and now I have here the next tree. And now because of this, it is now this actually we have here now the time with temporal dependence. The temporal dependence, and now it means I have here the dependence between time point 1, time point 2, and again I shift it in this way. Okay, you go and so on. The idea was very easy. Start from time point t equal 1, copy it. Time point equal 2, I mean 2 of them after regress copies and so on. Yeah. Yes, and what means translation invariance, this copula should be the same, this copula should be the same, and so on. It means very easy assumptions which you can check here. I mean what you see here, this is necessary for the stationarity, but we don't know it's not sufficient. And it's a very practical solution. Yeah. And what we have also T1 theorem, translation invariance. Yeah. is sufficient for stationarity. I mean, it means if I assign for each H1 copula and do it to stationarity, I would like that at least invariant means that from each time point I will shift it, is sufficient if and only if the value to S1. For our ones, as we construct, you can show it. It is only other S1 copula is a marker point over the P. If all pair copulas such that for all AB given B, yeah, if that large, it will be the here to show it. I mean, if you have only this guy, you have this guy and this guy, then it will be autoregressive of order 1. Okay. If you don't have these guys, I mean, then it will be just IID independent. Yeah. And this is exactly what you see here. Is this theorem, second one. And here's now remark 4. So in general models, because you write down all variables as in one big line, you for this T equal 105, you have so many variables. For 1,400 dimension 20, you have 200 million almost, yeah. And if you assume now stationary model, what we said here up to time T plus and so on, you have still here 500,000 about, yeah. But if you put more permanent structure, then you will enter the substantive. And what's interesting, as well as some current structure, this doesn't depend on the time point, number of the time point. You put here 100, if you can 1,000, the number of the parameters is always the same. It depends only on dimension and P. And now, what I showed you, it was intuitive idea using the graphs. I mean, yeah, you just take it and copy it. And we can also characterize it using graphs. And for this, here you see the following. We recognize that what we have to do. You have one permutation I1 and ID, yeah, so compatible on the one mu. I mean, which is describes the cross-sectional dependence, yeah, and then it is so compatible if you each time, you consider K in there and this one you take out, you always have something which is in this level. The point is the following. I would like to stop maybe using this one. Following, as soon as you construct this one, you can connect these guys here. Yeah. In the next step, you could think, okay, I would like to connect this guy maybe for temporal dependence, but this will not work. So exactly this we achieve using compatible permutation. Compatible permutation tells you which variable next time could be connected to the cross-temporal dependence. Yeah. It's not something like what you get something from the out and say, okay, I will not connect it. And this is, and if you have this, we have the theorem, it means all S1s, the loop, this one, you copy sectional dependence, and then we can write down also all edges, you know, these two guys, E1, EK. Now, the model by Smith is the following. In his case, E1, ED, I have to make two of them, yeah? It could be D1 and G1, G1 there. What's actually E1? It's actually each time point T, from which variable should go out the edge. It goes always from D, the next one, D minus 1, and so on. And this guys describes me in which variable they enter. Enter is the variable 1, then is the variable T, also it's already here. Yeah, if I will consider the here. From variable D to variable 1, then appears variable, which of variable 3 appears, and then it's on. Okay, and it goes with variable 1, then it goes to the variable 12. This is the point. Okay, and now we see here that we can describe it, and now we just consider our model. It means in our model, I can just choose this permutation, and this blue colors means actually, first of all, it goes out from the variable 2 and enters in the variable 3. The next step, it goes out from the node where the variable 1 appears for the first time. It's here, yeah. And this guy goes in where the variable 4 appears for the first time. And the next 3 would be here. Now the next one 3 appears. I can connect it. And I think starting from here, you don't have any freedom. You need to determine where you would have freedom. You would have freedom. Okay, this was exactly actually how we can construct these lines. There is a package which fits this model. Just recently, one master student put code everything for the S lines with variables. We can also do for these variables. It is not publicly all available because he's testing at the moment. And to estimation, I mean, the estimation part was mostly done by Thomas Nagler because he was interested in how you do here. Actually, you have the original variables by estimating distribution function, parametric or non-parametric. You get the so-called pseudo observation. Pseudo observation estimate Copulas. densities. I know Copulas can know what the distribution function, so you can compute the quantity. And you just continue this sequential, yeah? It could be many times, and sequential estimation is actually here. And what if you do the sequential estimation? I present the result only for the parametric case, non-parametric case was done also in the paper. What you see here, the other sample delta samples, the sample theta for the marginal parameters and theta for the focal parameters are converged in probability, yeah? The true values, and we have also asymptotic normality. J was expected efficiency measure matrix, I is the expected Hessian matrix, yeah? We can show it, and these results are actually even new. If even you consider inference for margin, but what Hydro did, he did a two-step. You have margins and you estimate couple of parameters, but we are doing here several steps. Something yes, you can also use it for the predictions. For the predictions, why it's good, because if you have amplitude xt minus 1, then you put out the predict xt plus k, if it's the order of after the k. Simulate this guy because I have the model, but simulate this model, maybe you're into some functional new star, which is and for this also new head, you can also show that it is you can also affect normal and understand regulator something. Otherwise, you know this regulator something on 1-2 pages. And 5 minutes is then maybe very short data analysis. What we consider it actually we consider certain components from the finance, this data points, these companies, yeah. What you see in European countries, companies from the European Union. We have also Chinese companies, and we have also insurance, automotive, IT, oil, gas, aerospace, yeah. And now what we did here, we compared S, M, and D1. We considered of all the people one because we saw that the high order, no difference in the empirical result. Yes, we model serial and cross-sectional dependence jointly for the marginal distribution considers T distribution, subset observations, yeah, or Blitzing transform. Yes, we consider bias structure, there is so-called Disman algorithm, and Copulas selected using the effective imaging criteria. And the benchmark model, we choose the VAR, gas line model, and classical what we see here. Because the armor guards in the model is the lines, and GCC guards model for mounted T injections. And this was the first three for the M and D line. It is not surprising because M and D lines, they usually always consider one long one, same companies. What you see here, if you put it this way, then you cannot actually express geographic location of the companies and maybe also the branch of the companies. Yeah, automotive or IT or insurance. If you consider M1, then you should connect in Airbus is Airbus with the highest dependence. If we do D1, then you do now with M1, with S1, then you see here we get this picture of the trees, and now you see here. So I think I don't remember exactly, but as this, what you see here, usually 1, 2, 3 of insurance, if you remember, yeah. And yes, you can recognize the geographic location, and you can also see some companies are from the same industry. If you check this in sample model comparison shows that the S line was pretty better according to the packet, and it was the best fit in sample fit. But if you consider out of sample prediction, we get here continuous rank probability scores of T1 and just look like we put in the trees, and here you see all models, and here you saw that for the 199, this one was better, but for the 1 week prediction, it was not so good. And otherwise, here you see here that it is not all the best one, but again, we are still looking very good applications for the S lines. And here maybe some what futuristic they are doing. So optimal structure and one bootstrap, I mean, the estimation of the sympathetic variant is very time intensive, computation intensive. We don't want how to do it. We consider factor models, yeah. Then we can also multiple discrepancies, and we also try to model now long memory with the S5. Yeah? But we can talk about this maybe after my talk if you have. That's all. Thank you.